So first things first, this is an R Markdown notebook, or an R notebook, I suppose. If you use R Markdown, it probably looks familiar. The syntax is exactly the same, and right here I've specified that I want to output to both an HTML notebook and then also to a GitHub document, which could be alternatively a PDF or an HTML or whatever. The GitHub document option gives you a Markdown file that displays nicely on GitHub. If anyone wants the materials for this, the repo is at my GitHub at tidyverse_talk. And so this tidyverse.md is the GitHub output. So specifying GitHub document in the output produces this markdown file, which then displays nicely on GitHub. And then the HTML notebook, this is still a little bit beta-y, but it looks like this. So it has all these code chunks in the outputs, and you can hide the code and reveal it, and it prints in nice ways, and it's like interactive. You can like scroll through tables, which is similar to how it displays inline as I do things. So I'm just going to walk through this, and then you can visit that afterward if you want. So what is the tidyverse? It's the new name for the Hadleyverse, per Hadley's request. And the idea of the tidyverse is that it's a suite of tools that all use a consistent API and have kind of a consistent philosophy, right? This philosophy of tidy data. Tidy data, you're probably familiar with. The idea is that each kind of observation gets its own table, right? So we don't we use relational tables. Each variable gets a column, and each observation gets a row. And then tidy APIs adds to that and says that we should, it's a literate programming idea. The idea is that every step in your code should do one little thing, right? And all of these tidyverse tools are written so that each function does one specific thing and does it well. And then we can string together multiple steps with the pipe, which is largely made possible because of this consistent API. So most of these functions take a data frame as the first argument, which allows us, and produce a data frame as an output, which allows us to just send data frames through line to line to line. And then is working towards this idea of referential transparency, which is like variable scoping, which is the idea that you should be able to look at a block of code and know entirely what it does, regardless of the environment that it's in. Right, so all the variables should be locally defined, which is not currently true of all tidyverse tools, right? Especially the like non-standard evaluation things. But Hadley is working in that direction. Hadley and this whole team is working in that direction. So what actually is it? It's about 20 packages. Here are the core packages, some or most of which you're probably familiar with. So I think of gplot, dplier, and tidier as like the real kind of old core of the tidyverse. Tibble you might be familiar with. It's what creates table data frames. I'll talk about that in a minute. Reader is for input and output of flat files like CSVs and text files. And then per, I'll talk quite a bit about per. How many of you have used per at all? Yeah, I just started exploring it in advance of this talk, and I'm pretty excited about it. It's got some really nice convenience functions, and I think everyone's still figuring out just what we can do with it. It's kind of like dplier for lists. It's kind of like there's an lapply replacement function. It does a lot of the dplier kind of stuff, but with lists. And there are tools for specialized data manipulation. So HMS for times, stringer for strings, lubridate for dates, and forcats for factors. All kinds of packages for specialized data imports for interacting with databases, with JSON files, to scrape data off the internet, to work with XML, and then modeler and broom to work with statistical models. And I'll introduce broom a little bit. I haven't played with modeler. I don't even know what it does. Installing the tidyverse installs all of these 20-ish packages. Library tidyverse just attaches these core packages, which is nice. I used to have like 3 or 4 of those at the top of all of my R files, right? So Library tidyverse attaches those. If you want to use any of these, if you want them in your search path, you can attach them individually. Okay, why tidyverse? Consistency. I think this is huge, right? Like the stringer package is particularly exemplary of this, or perhaps the base R functions are particularly exemplary of what we don't want, right? Like in the base R, regex, and string manipulation functions, I can never remember if like the string goes first or if the pattern you're matching goes first, if it returns a list or if it returns a vector, because it's not consistent across all these functions. Stringer makes all those things consistent. Like I mentioned earlier, almost all of these functions take a data frame as the first argument, which is nice for consistency, and it also enables this piping, which makes code faster to write and easier to read, which makes it less bug prone. They all work well with tidy data, which imposes best practices, right? If your plotting software requires your data to be in the best practice format, then you'll keep your data in that format. And then also it supports type stability or type specificity, I think is what I actually want to say there. Specificity. The idea there is that you can specify on a function, I expect this to return a logical vector. If it's anything but a logical vector, stop, right? And so especially for programming, that's useful. You can say, I expect to get something here, but if the result is null, I don't want you to keep going, I want you to throw an error. And that's built into a lot of these tidyverse functions. You probably use some of it already, like dplier and gplot. Adding other tools fits well with that. A lot of this stuff, all of this stuff is doable in base R, right? All of this is just convenience. But just convenience is a little bit ridiculous, right? Like R is just convenience over C++. C++ is just convenience over assembly, right? Everything is just convenience. Tidyverse takes it one step further beyond base R. R is old and based on S, which is even older, and some of the defaults don't make a lot of sense for the way that we use it today. The tidyverse implements what are generally seem to me to be smarter defaults. So for example, write CSV in base R in the utils package writes the row names as the first column in the CSV. Most of us don't use row names, and every time that trips me up, and I end up with this extra column of just the integers of my rows. Right? So write CSV doesn't write those. Cool. It's fast. It's generally faster than base functions. It's mostly implemented in C and C++ under the hood. And then importantly, it interfaces nicely with other tools. So dplier, for example, can be the front end to a whole bunch of different database backends, including like Spark databases through the Sparkler package. So you can interact with Spark backends through a consistent syntax that you already know based on the tables that you learn during your PhD or whatever. All right, with that said, I will attach the packages. So in our notebooks, if you put your cursor inside of a code chunk and hit Command or Control Shift Enter, it executes that whole code chunk and then displays the output right here in line. When you attach the tidyverse, it prints out which packages it's loaded, and then it prints out conflicts with other packages. So it's saying that filter is the search path is going to hit the dplier filter before it hits the stats filter. It's nice to know. Tibbles are a modern reimagining of data frames. So I create a data frame here that's got the first 10,000 integers and then 10,000 standard random normal numbers. This is the same as data underscore frame. So a lot of these functions rewrite base R functions with an underscore where there is a dot in base. So data underscore frame creates a data frame that has these additional classes, tibble and tibble diff. And they implement a few nice things. First of all, they print nicely. So this is the R Markdown display of a data frame, but I can do this. If you just enter the name of a tibble, it only prints the first 10,000 rows and however many columns fit on the screen, and then it tells you there are more rows, which is nice, right? Rather than seeing 10,000 rows scroll by. You can customize how many rows it prints with print. So I go print dibble n equals 30, tibble is not my table, that's the class. Print TDF, then it prints the first 30 rows, and you can set default options. If you want them to print all the rows or all the columns or whatever, you can set that globally. They, like with the write CSV, they implement some nice defaults, so they don't make strings as factors. So what I'm doing here, I make a list of 2 data frames, one with baseR's data frame and one with tidyverse data frame, and I'm going to show some differences between the two. So all of these I s-apply over the 2 data frames and ask, first, what is the class of this ABC column? So this column is just the first 3 letters in both of the data frames. In baseR, that gets converted to a factor. In the tidyverse, it stays a character vector, which might help you avoid running into bugs further down the road. Tidyverse does not use partial matching of data frame and list names, which is nice. You can get bit pretty hard by this. So if we ask for, so remember we have columns ABC and XYZ. If we ask baseR for the column named A with the $, it returns the ABC column. Tidyverse says, nope, we don't have a column named A. And then type consistency. So here on both of those data frames, I use the 2-dimensional square bracket subsetting to pull out the ABC column or vector. Using single bracket subsetting, tidyverse always returns a data frame, a table data frame. baseR returns either a vector or a data frame, depending on how many columns you pulled out. Right? So this type consistency is nice for programming purposes. You know you'll always get a data frame back when you single square bracket subset a tibble. Note that this can break existing code. So in one of my projects, I switched from read.csv to read_csv, which converted my data frames into tibbles, which then interacted differently with code that I had already written. So do be aware of this. List columns. I'm pretty psyched about list columns. So here I create a tibble where the first column is the integers from 1 to 5, and then the second column is a list of 5 objects, and it prints like this. So another nice thing about tibble is it gives you the type of data in the vector in the default print. The first column is these integers, and then the second column is a list of varying lengths of class double.
Can you give a use case for that?
Yeah, we'll get there. You can keep. So I often do simulation exercises where I have parameters in columns and values in rows, and then I simulate like networks or data sets. And now I have to keep those in a separate list, which is then detached from the data frame. So if I then subset, I have to subset the list based on values in the data frame. Now I could keep those simulated data sets in the cells of the data frame and could filter based on the parameters, can keep the output in the data frame too. I'll show some examples of that. The pipe sends what's on the left of it. So this is the pipe, percent greater than percent. It sends the output of whatever's on the left to the input, the first argument of whatever's on the right. By default, you can specify it goes to other arguments of the thing on the right. So here I add the numbers from 1 to 8, take the square root, which is 6. And I'll use that extensively through the rest of the presentation. It makes these tools code, I think, much easier to both write and read, and to build up iteratively. Right? You can start with the first steps and then add steps on and add steps on, rather than starting from the inside and kind of building code out and like wrapping more and more parentheses around it. It also keeps arguments together, right? If you're building code from the inside out, then you have one function here, and then you have the outer function here, and the arguments to it here, and then a function here, and arguments here. Whereas using the pipe keeps, function, argument, function, argument, function, argument. Makes it easier to read in that regard also, and hence less bug prone. dplier, does anyone here not use or know dplier? Okay. I'll demonstrate it briefly. I think its adoption is pretty widespread already, but go ahead and demo it. So ggplot2 movies loads this data frame of 59,000 movies, the year they were released, their budget, their rating on IMDb, the number of votes they have on IMDb, some genre details and specifics of the distributions of the ratings. So dplier it has a lot of convenience functions. It has like 4 core convenience functions that do, again, things that you could do in base, but makes them maybe a little bit easier to read, and it does make them faster because it's all implemented in RCPP, in C++ under the hood. So I can filter the movies to those that are longer than 6 hours.
Michael, you keep saying it's faster.
Yeah.
But in my experience, most of Hadley's stuff is there's a very deep call stack. So how is it faster with a deep call stack?
So like
most of
ggplot
is in C.
I don't think so. Well, I have a test further down for something, but let's go ahead and do a test here. So this will be very, very fast regardless, but system time movies where movies length is greater than 360, all columns. Yeah. So ggplot is not, and it does use a really deep call stack, and it's pretty slow. And I know Hadley's working on that, especially as he moves towards interactive ggplot. Some of base R is implemented in assembled code too.
Most of like subsetting the bracket operators.
Yeah.
A lot of the Boolean operators are all C. But I'm curious because he keeps saying that, but I in my limited use of this, it's actually slower.
I will demonstrate that it's faster later. I mean, and this actually is, I think, pretty widely validated. I mean, I can't speak to how, but it is. Okay, so stringing together functions with the pipe. So this filter to where length is greater than 360 outputs this data frame of just 21 rows. So filter is used to subset rows like I did over here in base. And then I can pipe the output of that to the select function, which also takes the data frame in the first argument. So I leave that first argument blank. And then I say I want to select the rows named title, rating, and votes. And I get just those. Arrange is used to sort a data frame by one or more columns. I think significantly less cognitive overhead than using the order function in base. And so order is not implemented in C, right? Whereas arrange is. No, because it's got that bytecode. Yeah. Well, but a lot of it is in R.
Yeah, so a lot of the checking for types and everything is in R.
Right.
Those are also if else, so they don't. It's not entering into that part of the loop or that part of the code unless that whatever is satisfied.
Right, but it is executing those checks in R. And we could do another test, but
no, it's doing a lot of the overhead is in R, except it's inside the if statements.
Right,
so
but it is executing those checks.
Yeah. But those checks themselves are in C. Like it's calling to the bracket operator.
No. It's executing this in R.
Right, but if you look at all is in C. I'm just curious. It's not a big thing, but I keep. It's not something that I understand how it is fast. Right?
Yeah.
And you have said yourself that maybe it might not be faster in some situations, right? It's more about it being readable.
I think that's true. I mean, it is more about it being readable, right? If you want pure speed, then use data table. But for the most part, despite the simple syntax, it is faster than base R, and I don't know how, but it is. And I will demo that later with PER's version of lapply versus base lapply. Here, the fourth and niftiest, I think, of the dplier functions is summarize. So this does what like aggregate and tapply do in base. So I'm taking the movie's data frame, I filter it to where it has an MPAA rating. That's like whether it's R or PG-13 or whatever. I group it by year and MPAA, and then summarize says within those categories. So within all the combinations of year and MPAA, I calculate the average budget and the average rating, and then arrange that descending by year and then by the MPAA rating. And so now we have just 128 rows for all the combinations of year and MPAA. Count is a shorthand for that, for rather than having some function to do on each group, just counting the number of entries in each group. So it creates a frequency table. So here we get the number of movies, animated or not, within each rating, within each year. And notice that this outputs a nice clean data frame. You can read it easily. You can take that forward and do something else with it if you want. Whereas in base, here's what that looks like, right? It's the code is like arguably harder to write and read. And then we get back this three-dimensional array. And if you want to even look at it, it requires some funky subsetting. And if you wanted to do something with it, I think year is going to be like the row names here. You'd have to convert it into a data frame, carry those over. You'd have to, combine the two dimensions. It's quite a bit harder to work with. dplier also does joins. I mentioned earlier that it's that one of the advantages is that you can then hook this up to different backends. So dplier does like database joins. You can interface to SQL databases, to Spark, to all kinds of different things. Here I create two data frames. So this first one has the first 6 letters and the first 6 numbers. The second one has the 4th through 10th letters and numbers. So that's what the first table looks like. That's what the second table looks like. And I join them together, and it matches on this name that I specified. And then just illustrating a little bit of detail here, I give it suffixes since both of the entry data frames have a num column. These suffixes get applied to the one from the first table and the one from the second table. This is neat. I stumbled upon this based on a student's mistake in a data carpentry workshop. You can, so usually we use group by and then summarize, right, to aggregate within a group. If you go group by to mutate, it does the summarizing operation and then does like a join of the output onto all of the matching rows in the original data frame. So I make this little goofy data frame. It's just like some letters as labels in the first column and some numbers in the second, group by group, and then put the group average in a new column. And so it groups all the C's together, calculates the average value, and then appends that on as a new column, repeating within the group. I thought that was pretty neat and really cool that I learned about it through a student's mistake. Tidier is the latest incarnation of Reshape, Reshape 2. There are a few functions in tidier. The one that I use more than all of the others combined is gather, which we use to take wide data frames and make them long. So we use to take data frames that are not in tidy data format and put them in tidy data format. So I'm going to demo this with this WHO tuberculosis data. So this is 60 columns, 7,200 rows, and the columns are a mess. So for every country and year, this is the number of new cases using the SP detection method for males age 0 to 14. So these are not variables, right? Those shouldn't be columns. Use gather. I'll make 2 new columns. Their names will be group and cases. And then the other arguments are to specify which columns I'm gathering up. And here I'm saying gather up everything except for these first 4. So the former column names of the gathered columns will become the group column in the new data frame, and the values here will become the values in the cases column in the new data frame.
Why is it raining?
So that gathered that up, we now have a variable called group and a variable called cases, and now we're in tidy data format, and this interfaces nicely with all the other functions. ggplot2, I'm not going to really teach ggplot2. That we've had 4 other talks here in DRUG about ggplot, and there's plenty of resources on the internet. Here I'll just show that it plays nicely with these other functions. So I do that same sort of gather thing on the WHO data, and then make a frequency table of it by country and year, and then plot a line for each country over time. ggplot's awesome. I think you know that.
What happens when one row has multiple entries? Like, let's say there's or is that not possible in the data?
What do you mean multiple entries?
If there was one entry, let's say row 1 for 10, 15, and 15, 24 both have entries. When it mutates or groups or whatever, isn't it?
So that it's, if I'm understanding correctly, that would not be tidy, right? If the variables there are sex, male or female, and age 0 to 14 or 15 to 25. So those should be columns. There should be a sex column and an age column. So here, I do that later on. Here I'm keeping all 3 of those together: the detection method, the gender, and the age, and calling that one variable. But in order for it to be tidy, we only have one value on each row. So the value in this case is the number of new tuberculosis cases, which is NA for these rows. Where is it not NA? It's NA for a lot of rows. So
your count function is also gathering, or like not gathering. Find a different word. Is it not summing based on year?
Correct.
In the count thing, the count function further down.
Yeah. So the count function here, it assembles all the unique combinations of country and year.
Yeah.
And then it sums the number of cases. This weight argument sums the number of cases. It counts the number of cases within each combination of country and year. So that, I should show you the output of that. So that looks like this. So there's never going to be multiple cases within a row. And if there were, it wouldn't be tidy data. So ggplot wouldn't want to handle that. Okay. Reader, here's a demo for you, Matt. Reader reads flat files like CSVs and text files and whatever else. Here I make a data frame with the numbers 1 to 1,000,000, the squares of them, and a bunch of letters. Write that CSV using the base function. It takes about 5 seconds. Write the CSV using the tidyverse function, and it takes 2.5 seconds. So in that case, it is faster. And then demoing those smarter defaults. So here I'm taking the CSV that I wrote using base and reading it using base, just reading the first 3 rows, and I got that annoying column of row names, which I never implemented, right? Like I never said to use row names or anything. The tidyverse versions don't do that. Cool. Okay.
What was the issue you said you ran into with read underscore CSV? That it automatically or defaults to a tibble?
It defaults to a tibble, which then interact differently. So like then your square bracket subsetting, you will always get a data frame out. Whereas there was a place in my code where I was expecting a vector from a single column name.
Okay. So how did you end up fixing that? Or did you change the arguments in read underscore CSV, or did you just keep read dot CSV?
No, so I like that square brackets in the tidyverse always return a data frame, and double square brackets always return a vector.
Mm-hmm.
So I changed that downstream
code.
But you could certainly use read underscore CSV and then do as data frame, and it'll convert it back to a regular data frame.
Okay.
And then it'll behave as expected.
This might be a dumb question, but I never remember when dealing with lists whether you use a single or a double bracket. Does doing it in the tidyverse affect that?
Yeah, so we'll talk about this a little bit with per. So per has functions that say explicitly, I want a list back or I want a vector back. And if it's a vector, I want it to be a vector of numbers. Like I'm expecting numbers. If it's not numbers, throw an error. In general, the rule is you can extract from a list using double square brackets. You can extract one element, and then it's and then it's whatever was in that element. If it's single square brackets, then you always get a list back, and it can be one or more elements. Broom is well, I don't know what all it does. It seems like a simple little package to me. It is for working with model data. There are two functions that I find useful. I'll demo them real quick. So I make a data frame here of some x values and some y values on a function with some noise. So Broom isn't in that core suite of packages, so I attach it explicitly. Create a linear model of the data, and then this tidy function pulls out the summary information from the model and puts it into a data frame. So like the count function from dplier versus table, this always puts out a data frame, which then you can work with downstream, right? Whereas the summary output from a linear model is like, I don't even know what it is, right? It's probably summary class or something.
And I imagine that's limited to certain types of models.
It's always a list. It's actually super extensive. So it works with my weird social network statistical models. I tested it last night. It doesn't work with Richard's rethinking models,
Yeah.
but it works with almost everything. It's pretty extensive.
Actually, I've written some really hacky code to put the output from Richard's stuff into data frames. And Dave Robinson, who's the maintainer of the Broom package, is always encouraging people to like send pull requests and patches for those packages. So if anybody else wants that to happen and wants to do some code review, then
Yes.
that'd be a fun like Friday project.
That would be. That's a good idea. And I'll demo this use in a pipeline. The fact that this outputs a data frame then makes it useful within these pipes, right? We could imagine building a bunch of linear models and then getting a bunch of data frames back, and then we can stack them on top of each other and continue with our analysis. The other function from Broom that I use is augment, which you may know as fortify. You give it a model, you can give it a new data frame, and it gives you predicted values, residuals, Cook's distance, lots of useful things. Here I demo doing this. So aug is this data frame with this additional information from this model, and then I plot. What do I plot? The x's and y's colored by the residuals just for fun, right? The high residuals are above the line, the low residuals are below the line. If you don't know, I'm not sure how you say this, viridis?
Yeah.
It's awesome.
That's
It creates color scales that are friendly to all forms of color blindness and that print well in black and white. It's a great color default. And it is built in. It has functions for gplot, so you can do scale color viridis.
Could you do something where your scale would be, like on here, if I wanted to see everything that was above one absolute value of one, right? Could you do that where you would set? I'm sure you could.
Yeah, sure. The easiest thing might be to create another column in the data frame, and then you'd have like a true and false column, and you could map that to color.
Cool.
It also has 2 or 3 other. It's like plasma, magma, and
Yeah.
a few. Two
They all make me feel like I'm in the third circle.
Right. But they're for different color scales, but they similarly they play well with printing and lots of other things. So.
Here's another example of what you might do with that augment output. So this is a standard sort of model diagnostic plot of the fitted values against the residuals. We don't want to see patterns here, right? That would indicate patterns among the errors, among the residuals. And then I size the points to the Cook's distance, which is a measure of how much influence each point has on the model. You can do model diagnostic stuff with this augment function. Okay, on to purr, which is kind of the meat of the talk, and I'll move pretty quickly here. So purr is kind of like dplier for lists. Here's a quick demo of some of what it does, and then I'll walk through a bunch of this in more detail. So I'm creating a data frame, or a tibble here, where the first column is some functions. So there's 4 rows in this data frame. The first column is lapply and map. Map is purr's version of lapply. So I'm putting functions in the first column. In the second column, I'm putting either 10,000 or whatever it is, 100,000 or 10 million. And then in the fourth column, I'm calling these first 2 columns, which is one nice thing about data underscore frame, is that you can use variables that you've just built in that same call. And I'm using this map2 function to access both of these columns, use this function to take the square root of all of the numbers from 1 to either 100,000 or 10 million. So 1 and 2 are on 100,000, 3 and 4 are on 10 million, and 1 and 3 use lapply, and 2 and 4 use map, use the tidyverse version. So a couple of things to note here. First of all, this is a column from a data frame and it's a list. That's cool. Also cool is that here's the function column. It is a column of functions in a data frame. And then notice how much faster map is versus lapply. Last time I did this, map is faster. I expected it to be slower for the smaller set.
So what happens if you call it outside of this, wrapped in a data frame inside of map2 inside of?
We'll get there. I'm gonna walk through from the ground up.
Can you just call, sorry, just really quick,
Yeah, sure.
type of or class on that first column?
And please do interrupt with questions. Sorry. Say again.
Can you call just type of or class on that first column of the functions? I'm just curious what class that column is.
Anyone want to guess?
Character. I don't know. List. Huh. Lists of
Yeah.
lists.
It's a closure.
Huh.
I don't even know.
It's a function.
Why they call it?
Closure.
Take stat 242. Yeah. Okay, so map is very much like lapply, and you can use the same syntax as lapply. So take the numbers 1 to 4, take the log of each. Fine. You supply additional arguments to the function, just like in lapply. It has this convenient shorthand for, so like in lapply, you can do this function of x, and then you can use x however you want in the anonymous function that's created. It has this formula syntax. So this specifies that you want a function of x, and then you can use either .x or just dot as your reference, as the x. So here I'm saying for the numbers 1 through 4, take the log of 4 with the base of the items that we're mapping over, and I don't have to specify the as a function of x. So it saves you a few keystrokes.
Can you do multi-line functions?
Yeah, like with the squiggly braces.
Oh.
But I think the tidyverse philosophy would be to write the map on each line, to output the data frame from this line, map it through to the next line, map it through to the next line. I think. But yes, you can. Okay, type specificity. So map double it's kind of like an sapply version of map. And here I'm saying I expect to get a double, a numeric value back. And it returns a vector, not a list, of doubles. And if you don't get the type you expected, so here I'm saying I expect an integer. These, of course, aren't integers, and so it throws an error, which is really nice for our programming, right? Map2 is like mapply. So here I create two lists. So vectors work like lists in lapply and in map. So 1 to 10 forward, 1 to 10 backwards, and then apply over both of them and take the first one to the power of the second one. So this will take 1 to the power of 10, 2 to the power of 9, and it goes over all of them in parallel. There's also a map_n function that generalizes this. So you could have a list of 4 lists and go over all the items in those lists in parallel. Map_if takes 3 arguments. So the first and third are like regular map. The first is a list or a vector or whatever. The third is a function. And then the second is some kind of logical test. And it can be a function that gets applied to the things you're mapping over, or it could be a Boolean vector, or it can be a few other things. So here I make a data frame that looks like this, and then, so when we map over a data frame, it treats it like a list, right? It gives us each column in turn. So the data frame is the first argument to this function. The second is this test. Is it numeric? And if it is, then return the square of the values. And if it doesn't meet that condition, it returns the original values. So it goes over this list of 3. For the 2 that meet this condition, it does this function. For the ones that don't, it just returns the original item. Okay, let's do some cooler stuff with this. This is a pretty contrived example, but I think demonstrates some of the power. So I take that movie's data frame, filter it to where it has an MPAA rating, split based on the rating. So split is a base R function that creates a list of data frames based on the values in the MPAA column. So we got a data frame of R-rated movies, a data frame of PG-rated movies, etc. On each of those, run a linear model. This dot is specifying, it's like the dot x, right? I'm providing the data frames in the first argument coming through from before, and then I'm saying put each of the data frames here in turn. Map df is like it's like lapply and then do call rbind. Takes the output from lapply and row binds them together. So I run all these linear models, then I call tidy from the broom package on each. So tidy will give us, I should be running each of these to show you how this is working. So this gives us 4 data frames. Notice how our Markdown notebooks displays that. So here's the 4 data frames. Scroll through them. This executes a linear model on each. So there's the results of each linear model. Then I say call broom on each of those. So we're going to convert each of those model results into a data frame. ID uses the names in the original list to create a new column that identifies which came from which. And then I sort it by the second column. And we can see that for R-rated movies, every extra $800 million you spend gets you an extra point of rating on IMDb.
What's behind the syntax of the dot ID in the map data frame?
So that's just an argument to map df. And it's just what to call the identifying column. It's just the name to put on the column, and this will take names from the original list that you provide.
Okay. And
So,
then why is the dot x a thing? Why?
the dot here.
Yeah.
So this dot here and this dot on ID are totally separate.
No, yeah, I get that
Okay.
dot. I get the data dot. I don't understand just why he's written the map functions as like the arguments have dots in front of them.
It's just a style thing. They could just as easily be X, F, and ID. just to keep you on your toes. Well, so one thing is that you then use .x to refer to the elements of x. If you use the function notation.
So it's something that allows you to call things that you just created.
I don't think it's enabling anything. I think it's really just a style. Okay, so I mentioned this earlier. List columns make organizing things really nice. Here I do kind of like I did earlier. So I'm creating a data frame and using previous columns as I go. So first column is these names of distributions. The second column is the functions that create random distributions of those names. In the third column, I map these functions. So loop over the functions. And then so the tilde is that shorthand notation for function of x. And then the x is going where that dot is. So this would be the same thing. So it puts the function there. And so it calls, the first time through, it calls R norm, and we want 100 with a mean of 5. Second time through, it calls R pois, I want 100 with a mean of 5. Then map to double, so I want to go over these values and find the mean, and go over them again and find the variance. And that's what that looks like. And then I include this just to say, like, if you later decide that there's some additional value that you want to calculate, look, I still have all these samples, and they're right here in the data frame, and everything is still organized. So I can tack on another column, and it's all associated with the data that generated everything. If we filtered in the meantime, everything's still organized.
So wait, how? So you're calling you're calling to a column in the data frame that you are creating.
Yeah. So here,
That is some funky stuff.
Well, it's all local to this data frame function.
Right, but so the order is the order important? Does it?
Yes, I couldn't move this up here. Okay, let's do something a little bit cooler with this. Stick with me. So I'm gonna. You guys know the diamonds data set? Yeah, everybody knows the diamonds data set. So I'm gonna fit a model using every combination of two variables from the data set to predict price and see which one works best. So I pick out 2/3 of the rows to use as my training sample, and then I use the other third as a test sample. So I'll walk through each line of this. So that just picked out some rows. Set diff, I'm saying give me the names in diamonds that aren't price, or aren't in this second argument, so that gives the names. Combin, so here I say give me all of the combinations of two items from this, and then paste them together and collapse with a plus, which I'll then use in formulas. So that's what that looks like. This line is a little bit weird. I want to use these as names later on, so I'm going to do that same thing where I call mapdf, and I want some identifiers. So I need to kind of pull these out as character vectors and use them as names. So this just gives each thing itself as its name. Then execute a linear model with the formula being paste together price underscore and then this for each of those, right? And that's the familiar linear model syntax. Execute the model on the training data set. Then augment. So I want to get the predicted values for each model for each of the observations that aren't in the training data set. So augment. So see what I'm doing here. I'm calling the augment function on each of the models that are coming in from the previous line. And I'm giving augment this argument new data. So rather than having it predict the values on the data that we train the models with, I'm saying predict values for the test data set. And then I give it the labels that are the two combinations. Then group that by the predictors. So I group by that naming convention. So I'm grouping all of the test observations together within each model. And then I calculate the root mean squared error within each and sort them. That will take a little while because it's fitting like 40 linear models or something to 30,000 observations. And perhaps not surprisingly, the size and clarity of the diamond provides the lowest error to predict price. That's pretty cool, right? Like that's a lot of work in like one, whatever it is, 8-line set of code, and it's reasonably readable. Okay, a couple things. I'll go through this quick because I'm pushing an hour. Type stability or type specificity. I can't remember which is the actual word. I think I'm using both in here. But type stability refers to this idea that especially when we're programming, we should be explicit about what we expect back from functions so that if we don't get that, it doesn't cause some weird downstream error that we're not sure where the source is. It locates the error where things went wrong. Flatten is like unlist with two differences. One, it never recurses. So unlist you can specify whether to just unlist the first level of list or to unlist everything. Flatten always just unlists one level, and then you can tell it what kind of vector you want out. So here what do? I take the square root, negative square root, and 0 power of each of -1 to 3, and maybe you don't remember if you can take the negative square root of -1. So you say, all right, if I don't get a double back for each of the values there, throw an error. But it actually does work because it returns NAM. Safely. How many of you guys use try? Okay, cool. So safely is a new implementation of try with a couple of differences. So when you use try, you get back either a try class error object or you get the successful output of the function. safely always returns a list of 2 for each execution. One is whether it succeeded or failed, and the other is the output if it did succeed. And one of those 2 will always be null. It's a little bit hard to explain. I'll show how it works. So first I create this this junk list. So it's got some characters, it's got some numbers, and it's got a function. And then I say, safely take the log of each of these items, right? So it's going to succeed on the second item, and it's going to fail on the first and third. So where it fails, the result is null, and then it gives you an error. And where it succeeds, the result is the result, and for the error, it gives you null.
Is it a list of lists?
It's a list of lists because I used map on it.
Okay.
Each call to safely just returns a list of 2, right? And safely, notice this different syntax. So safely creates a new function. So safely of log creates a new safe log function, and then we call that with the argument .x. That parenthesis goes in a different place than in try. And then this is useful, especially with this transpose function, which I'm kind of irrationally excited about. So notice here we have a 3 list. Each item is a 2 list. Transpose flips that around. So then we have a 2 list of 3 lists, right? It like inverts a list. This is something that I want to do often, and it always takes more steps and effort than it should. So now we have a list of 2. The first is our results, and the second is our errors. And now we can plug along like with map if. So now I can say, go over the transpose version, this list that I just made, and if the result is null, right? I'm going over the results list. So if this is null, if it's not null, then take the median. If it is null, then don't do anything. Okay. And then briefly, stringer. Stringer is what really like pushed me to the tidyverse. Because the base R string handling functions are just so inconsistent, right? Like get back a list, get back a vector, don't remember which arguments go where, everything changes. Stringer is consistent. All the functions start with str underscore. The string always goes first, and then the pattern and replacement, if there is one, goes second. So, and they're named semantically. I don't have to remember what greg means, right? I know that I'm trying to detect a string here. So I look for 2 in fishes, and it is in the second entry. Replace all, we'll find all instances of fish and replace it with banana. String extract extracts the matches. So here I look for a number followed by a space and extract those, and I get it from each. And then last thing I've got for you, and this seems to have collapsed. Okay, I'm going to do some real work with stringer. So I'm using that WHO tuberculosis data frame. So remember those column names were kind of terrible, right? The column names looked like this. So they start with new or new underscore, and that doesn't tell us anything. It's just these are new cases. Then there's 2 or 3 letters that indicate the detection method, followed by an underscore, followed by a single letter for the gender, and then 2, 3, or 4 numbers, which are the age range of the subjects. So we're going to separate that out. So first, I gather it up like I did before. So I get rid of those country codes, gather it up, so we have country, year, the grouping, which is this whole mess of a variable, and the year. And then I go through and take out that new with an optional underscore. So the asterisk means with or without the thing that preceded it. So get rid of the new underscore and replace it with nothing. Then extract more than one letter, which gets me the code that's in the beginning, right? This is the only place where there's more than one letter. The gender, I string extract an underscore followed by a letter, and then take just the second character of that. So this extracts the underscore and the M or the F that follows it, and then I take just the second character of that with substring. For the age, I string extract more than one number, which gets me 014 or 1524, and then I have to do some more processing on that. So I say if it's longer than 2, I won't walk through all this. If you want to see how all this works, you can dig through it on your own. But pull out the numbers. If there are 4, then take the first 2 and the last 2 and put a dash between them. If there's just 2, which is the case for 65 and over, then just put a plus on the end of it. Then group those up and summarize, and I show just a little bit more of some of what ggplot does for funsies. So we've grouped by age, by the test method, and by gender, and plotted the frequency of new cases over the years. Mostly what we see is that this test method comes to dominance in 2012 or whatever, and the others stop being used. Cool.
Very
Sweet.
Welcome to the tidyverse.
nice.